Hi, Martin. How are you doing today?
Thank you. How are you?
Good, busy Friday, just like yours. Yeah,
Yes.
great. We're so happy to have you here as a research scientist and lecturer with ET at Zurich and a professor of environmental chemistry at the Masaryk University. Your work has been central in advancing our understanding of PFAS, and TFA is an emerging part of this new picture. So I'm really looking forward to digging into TFA with you today, this ultra short chain PFAS, and unpacking what the science shows so far and what we are still learning in the process.
Yeah, interesting and exciting.
Thanks, Martin. So, just to begin, could you briefly explain what trifluoric acid or TFA is and why has it become an area of scientific interest in the recent years?
Yeah, in a way, it is related to a chemical that everybody knows because that is acetic acid, which is a main component in vinegar. And we eat it and we know it. But trifluoroacetic acid has, in some part of that molecule, the hydrogen replaced with fluorine. And that changes the properties of the chemical a lot, and we can no longer really eat it, and it is toxic. And the main problem with similar to all other PFAS is it is super persistent. It does not degrade. There is no process in the environment that has enough energy to break the carbon fluorine bond, and that makes it a problem because will never go away.
Yeah. So when you say it's very persistent, how prevalent is TFA in our environment? Do we have any data and statistics to see if it's found in a big concentration? And where are the primary sources of this TFA where it's being
Yeah,
discharged?
unfortunately, it is prevalent. We have seen it for many years even now, but recently it has been even more in the discussion and also in the media. So we see it in all water bodies in Switzerland and beyond. We see it in food, and it comes from different types of sources, which also makes the picture a bit complicated.
Mhm.
One type of source is plant protection chemicals, pesticides that contain a part of the TFM molecule.
Mhm.
And when they are applied to the fields, then they, in the end, are degraded, most of them. But then the part that will form TFA in the end will not be degraded because it is a PFAS and can't be degraded. So TFA is a leftover of these chemicals that are on the fields even, and that's a direct source or emission pathway into agricultural soil and also crops. And another
Mhm.
source that's very different is from what's called fluorinated gases. These
Mhm.
gases are heat carriers, for example, used in heat pumps or in air conditioning devices, and there's always some leakage, so they go out into the atmosphere, and then in the atmosphere they are oxidized, as we call it,
Mhm.
and form also to some extent TFA, and then with the rain it comes down and it rains TFA. So in
Mhm.
addition to what we have in the fields from the plant protection products, we also have an additional kind of background contribution of TFA out of of the air from these gases.
Mhm. So quite a few different ways it ends up into the environment, right?
Hmm.
How does TFA differ from a long chain compounds like PFAS and PFOS for our audience, just so we can understand? Like apart from the chain length, is it something else that is very specific for TFA versus the long chains?
Yes, as you were saying, of course, the first thing is the chain length. It is the shortest chain that a PFAS can have. And that has some, of course, important or makes or causes some important differences. So it is less bioaccumulative, as we say. So it has a faster removal from the body.
Hmm.
If it's taken up, it's also released from the body more easily or more quickly. It doesn't stick with proteins in the body, so it does not bioaccumulate. But the problem here is it is always resupplied because we have new uptake from TFA in drinking water. So it doesn't really change the picture because we still have continuous uptake and resupply of TFA in the body.
Hmm.
So, but yeah, it does not bioaccumulate in the same way or
Hmm.
to the same extent. And it's also less toxic. At least the liver toxicity is much lower than, let's say, for P4. But it may have also other types of toxicity that are not yet fully elucidated even. I think recently there has been the observation it could be toxic for reproduction.
Hmm.
So it makes changes, causes changes in the newborn, and that's of course very that's concerning.
Yeah.
But it's a bit different. But of course also shares the property of being persistent, and
Yeah.
that is the root cause of lots of problems of all PFAS.
Hmm. So just to summarize that bit, so it is not bioaccumulating so much like the long chains, but because it is found in much higher concentrations in general, we keep ingesting them. So overall, it might have a very similar effect because it's a higher concentration, but less accumulative. And still gaps exist, but we also have some studies that are pointing towards not the best toxicologic effects on humans as well then. So obviously
Exactly.
very, very grim picture there and a lot of gaps still there, which hopefully the scientific community can get to in the coming years. Um, on this profile as well, so when we talk about TFA in the broader category of ultra short chain PFAS, are there any shared behaviors or profiles or noticeable distinctions of TFA with the other ultra short chain PFAS, or are they very similar in their behaviors, all of them?
In terms of behavior, I would say that it's gradual. So the chain
Mhm.
length gives us a gradual change according to the length in a way.
Yeah.
But TFA is different because of its the sources, because we don't have these sources for the other very short chain PFAS. So we don't have the plant protection products and the fluorinated gases as sources of similar
Yeah.
amounts of the other short chain PFAS or acids.
Mhm.
So
Mhm.
TFA kind of stands out because of this particular type of emissions that cause these high levels.
So it's a prevalence because of which TFA is so in the highlight today. It's not necessarily the other properties, just found more in
Yes,
concentrations. I remember
absolutely.
seeing the study, I think it came out last year in December, where the FOIN did this groundwater sampling of 550 different groundwater samples in Switzerland, and they found TFA in all of them. And that was I wouldn't say shocking, but definitely alarming. And I think we expected to see this, but all of them being such highly contaminated, that was definitely alarming statistic to come out of Switzerland and our groundwater. So yeah,
Absolutely. Yes, absolutely. And that's why my TFA stands out as a particular concern.
yeah, yeah. And are there any other blind spots, sorry, when it comes to TFA, like where research would be valuable to fill those gaps, where we have more blind spots and more alarming data maybe coming as well. So anything in particular that stands out to you that we still do not know about TFA scientifically?
I think something that certainly matters is toxicity. So I'm not a
Mhm.
toxicologist, so that's not really my area. But from what I have read and learned is that there's still a lack of better so long-term studies on the toxicity of TFA
Yeah.
in mammals and then transfer this to humans. Um, there has been have been some investigations also in the connection with the authorization of plant protection products, but somehow this knowledge is not really doesn't fully cover everything we should know now because of the alarming situation. So there's a call for better understanding of the toxicology, certainly. And also for some of these plant protection products, it is suspected or can be assumed that TFA is formed, but
Mm.
here also would be helpful to have an experimental confirmation that this happens.
Yeah, I see. On the same side, on side of blind spot, I always think what we can't measure is not a problem. If you don't know something, it's not a problem, right? So I'm always brought to the whole measurement analysis of TFA being such a big, crucial part of really knowing how prevalent it is so we can actually solve it. Are there any particular analytical or monitoring challenges that you are aware of with TFA or other ultra short chains that make their determination and environment more difficult?
Not really. First of all, I fully agree that this is a huge concern, this kind of it's a fallacy in a way to say no
Yeah.
data, no problem. So what
Mm.
we don't see doesn't exist. Of course, that is not true.
Yeah.
But I think for TFA, it is mostly, again, I go back to toxicity, to the toxicity side, where we don't know enough, don't see enough
Mm.
about the toxic effect it has.
Yeah.
From the analytical point of view, I mean, again, I'm also not an analytical chemist, so I can't really talk about the challenges in determining it, but it seems that we can clearly measure it now and see
Yeah.
what the levels are.
Yeah.
So I think that's not a lack of data or the understanding that we have. We see it's there, we see where it comes from, we see how much it is, but we need to know better and also be able to say more clearly what it does.
Yeah. I think on that, we have made tremendous progress on being able to analyze ultra short chains in the last decade or so. And I think that's also why we can now start measuring them in low concentrations. A lot of work still be done to improve the detection limits of ultra short chains, but what we already can measure is already quite significant, I think. So that's a great scientific advancement in this journey of ultra short chains. Jumping gears a little bit into policy and regulation, right? Because if we want to see a change around implementation or protection, we need to be able to also think about what policy and regulation can do to support that change. Most of the current PFAS related policies, if you see globally, they're really focused on long chain or medium chain PFAS compounds like PFAS, PFA. From a scientific perspective for you, how should policymakers really be thinking about ultra short chain substances like TFA?
Yeah, they should include them, and I think they are increasingly doing so. They should
Yeah.
also see them as part of the bigger PFAS picture. Of course, they are different, and many people often point out how different they are and all that. But again, they share the concern or the problem of being persistent or being super persistent, and that's also why in the EU there is the restriction proposal for uses of all PFAS, and I think that's exactly the point. Although they are so widely different in many respects, they still share this problem of persistence and, of course, also some type of toxicity. And that's why regulators should see the bigger picture.
Yeah.
But they may have to target or to tailor regulation, then, of course, perhaps to specific substances and their concerns. But I wouldn't say, or what should not happen is that TFA is seen as a totally different problem that is not connected with the other PFAS problems we have. It's
True.
not.
True. Yeah.
But
No,
it's a
I
challenge, of
totally
course.
agree.
It's a challenge. This
Yeah.
this broad scope of properties and of problems that need to be addressed. It is a challenge.
Yeah. I mean, if you look ahead 5 years from now, what scientific or policy developments would most advance evidence-based management of ultra short chains like TFA?
Wow. Um, of course, again, as we have already said, we need a better documentation of what they
Yeah.
do, that we have a stronger uh, basis for actually intervening, and also in the end, I think some of the chemicals that lead to the formation of TFA in the environment should be banned, should be removed, because there are replacements for the
Mm.
fluorinated gases. There are many other um, options, and many of them have been in use for long. So that can be changed. So that source could be closed, that emission source. And also for the pesticides, I think that there's now a new discussion about these pesticides that form
Mm.
TFA, that the authorization needs to be reconsidered at least, or perhaps even withdrawn. And Denmark has banned
Yeah.
several of these
Yeah.
pesticides just recently. So that's certainly the movement that we are seeing.
Yeah, so already quite a lot of momentum on that. That's really, really promising, right? On the other hand, I always find other momentum as well in the space where TFA is considered also like it's not even a PFAS. There's this discussion around it's not a PFAS, so it's not a problem. What is your scientific fact-based opinion on that? Is that a PFAS and should it be considered a PFAS within the framework of re policy and regulation as well?
Yes, of course. I mean, I would say, of course, it's a PFAS, because what PFAS means is a fluorinated, a perfluorinated alkyl substance, and that means alkyl is a saturated carbon. So, of course, it is a saturated carbon that is perfluorinated. That's what it exactly what the
Mhm.
molecule contains. So the definition is quite clear, but I'm aware of these discussions. And here, I think it's helpful to differentiate between a scientific definition, in terms of chemistry, really, what I just said, a perfluorinated carbon, and regulatory definitions or the scope of a regulatory measure.
Mhm.
Because in regulation, of course, regulators can always choose the scope of a regulation they want to
Mhm.
implement. And they can also target a particular type of PFAS.
Mm.
But they shouldn't say, oh, that's not a PFAS. They should see that the chemistry is clear, the chemistry is the chemistry, and that's the basis, I guess, for the judgment and assessment and analysis. And then regulators are free to decide on the scope of the regulation, because regulation doesn't have to follow the science one by one.
Yeah. No, thank you for making the clear distinction between a scientific chemistry definition and the language a regulator might choose to put into enforcement, right? It's
Yes,
very, very
absolutely.
important to distinguish facts from what can be
Absolutely. Yeah.
implemented.
And
Yeah.
both are in their own right. I mean, it's important to see the scientific definition, but also important to acknowledge that regulation is a political process that may make decisions that don't exactly reflect the science one by one.
Yeah, yeah, absolutely agree with you. And thank you for explaining that in a scientific manner for us to differentiate the two definitions. Looking forward, so in one sentence, what keeps you hopeful about our ability to be able to tackle PFAS properly?
Yeah, it depends really. I think there's different angles here. One, of course, is let's say the work that you do and colleagues of yours, because one challenge we have is that we need to be able to destroy PFAS, that we need to collect them where they are at the source, and then have technologies that help us to destroy them, get rid of them, and prevent their emission and spread out in the environment. That's certainly very good and very important. The second thing is, of course, that we should also try to avoid
Mhm.
even the generation of these PFAS in the first place and try to move over to alternatives wherever possible. And here we have a, let's say, complicated regulatory process, and we also have a transition, let's say a technical transition from PFAS to alternatives in very different applications,
Mhm.
complicated but also moving.
Mhm.
And the third part is really the PFAS that have already left our technical world and are now moving around, circulating in the environment, and that's where I don't see much hope really.
Yeah.
We can't take them back. It's like the milk in the coffee that we can't take them out of the lake
Yeah.
in your background of your that shows this nice lake. We
Mhm.
will not be able to take them back from the larger environment, and that is a
Mhm.
concern that we will
Yeah.
have that will be with us for long.
Yeah. So your hope is all around action based, what we can do today in that sense. Like let's replace what can be replaced, but stop treating what can be treated well today. So we stop injecting more. And hopefully there is at some point some solution for what we've already caused damage of in terms of remediation. But there's a grim hope in that sense. It's a big
Yes,
problem. Yeah.
yes, yeah, absolutely. That's very good as a summary. Yeah,
Yeah. Thank you so much, Martin, for sharing your honest feedback and your scientific outlook on the problem of PFAS. We need science to balance what is possible to be done, and we need that opinion. So, thank you so much for coming on this platform to talk about this problem. I really appreciate it, and I learned a lot of new things today. And I'm sure anyone who's listening also learned a lot of new things. So, thank you for your time.
yeah. Thank you for having me, and pleasure to do this with you.
Thanks, Martin.